Large language models, or LLMs, have revolutionized how we interact with artificial intelligence. However, one of their biggest limitations is their lack of memory. Imagine trying to have a conversation with someone who forgets everything you said the moment you finish speaking. That's essentially how LLMs operate. They are stateless, meaning they don't remember previous interactions unless you remind them. This creates a challenge when building applications that require context over time. In this video, we'll explore why memory is crucial for Agentic AI, the current solutions, and how you can implement robust long-term memory systems for your own LLM applications. To understand the memory problem, let's compare short-term and long-term memory in LLMs. Short-term memory is relatively easy to implement. You simply include a few previous question and answer pairs in each interaction, allowing the model to reference recent context. However, this approach quickly becomes impractical as conversations grow longer or more complex. Long-term memory, on the other hand, requires the system to recall facts, connect information, and understand previous conversations over extended periods. Building this capability is much more challenging and demands sophisticated solutions. A common first instinct is to simply dump the entire conversation history into the model's context window. While this might work for short exchanges, it quickly becomes unmanageable. The model struggles to identify what's important, leading to irrelevant or even hallucinated answers. As conversations grow, you also face technical limits on how much data can be processed at once. This naive approach highlights the need for smarter strategies that can efficiently manage and retrieve relevant information without overwhelming the system. The next step up is using semantic search, often implemented with retrieval-augmented generation, or RAG. Here, every message and its summary are stored in a database. When a user asks a question, the system searches for relevant information using semantic similarity. While this improves retrieval, it introduces new challenges: memory bloat, outdated or conflicting facts, and the need for regular database maintenance. As your application scales, these issues can become significant bottlenecks. To make memory systems more useful, it's important to track when things happen. For example, if a user asks, "When did you tell me about the first restaurant?" the system needs to understand the timeline of events. This requires adding metadata, like timestamps, to each message, and possibly building self-editing mechanisms that can update or invalidate facts as new information arrives. Temporal reasoning helps the AI provide more accurate and context-aware responses. As memory systems evolve, they need to do more than just recall facts. They must connect different pieces of information and recognize patterns. This is known as multi-hop reasoning. For instance, the AI should be able to answer questions like, "How many concerts have I attended this year?" or "What is my music taste based on past conversations?" Achieving this requires more advanced data structures, such as knowledge graphs, which can represent relationships between entities and support complex queries. Most advanced memory systems organize information into two main categories: pocket-sized facts and long-span conversation summaries. Pocket-sized facts are small, easily retrievable pieces of information, such as user preferences or profile details. Long-span memory involves storing and summarizing entire conversations, allowing the AI to reference past interactions. This dual approach helps balance efficiency and depth, ensuring the system can provide relevant answers without being overwhelmed by data. A practical example of this dual memory approach can be seen in ChatGPT. The system likely uses classifiers to determine which messages contain facts worth storing. These facts are then categorized, such as user preferences or projects, and either updated or added as new entries. For conversation memory, ChatGPT stores and summarizes entire exchanges, but users must enable this feature. Deciding how much detail to keep is crucial to avoid memory bloat and maintain system performance. One common architecture for long-term memory is vector-based retrieval. Here, documents or messages are embedded into vectors and stored in a database. When a user asks a question, the system fetches relevant vectors using both semantic and keyword searches. While this approach is simple to start with, it has limitations. Facts are immutable, so outdated or conflicting information can accumulate. Over time, the database grows and requires pruning or compression, which risks losing useful details. Knowledge graphs offer a more structured alternative. They represent information as a network of entities and relationships. allowing for more flexible updates and multi-hop reasoning. Instead of deleting old facts, knowledge graphs can mark them as invalid from a certain date, preserving history. Graph traversals make it easier to follow relationships and answer complex queries. However, as knowledge graphs grow, they require more complex infrastructure and can experience higher latency, especially during deep searches. Many advanced systems combine both retrieval-augmented generation, RAG, and knowledge graphs to achieve the best of both worlds. Pocket-sized facts can be managed with classifiers and categories, while long-span memory is handled through summaries and structured relationships. This hybrid approach allows for efficient retrieval, pattern recognition, and temporal reasoning, making the AI more capable of handling complex, real-world tasks. Several vendor solutions have emerged to help developers implement long-term memory in LLM applications. Zep and Graffiti use knowledge graph-based architectures, leveraging LLMs to extract, update, and manage nodes and relationships. Mim0 and Letta, on the other hand, are vector-based and focus on self-editing and summarization. Each solution offers features like categorization, core memory, and conversation blocks, allowing you to tailor the system to your application's needs. When choosing a memory provider, security is a key concern, especially for enterprise applications. For example, Zep is SOC 2 Type 2 certified, offering robust cloud security. Many solutions can also be self-hosted, allowing you to control your own infrastructure and security policies. As these frameworks are still evolving, it's important to evaluate their maturity, scalability, and how they handle sensitive data before integrating them into your workflow. Adding memory features to your LLM applications can significantly impact costs. Most vendor solutions offer free tiers, but expenses rise quickly as usage grows. For organizations handling hundreds of conversations daily, cloud pricing can add up. A common strategy is to start with a cloud solution for convenience, then transition to self-hosting or hybrid models as you scale. Implementing your own classifiers to filter which messages are stored can also help control costs and keep your system efficient. Even with advanced memory systems, perfection is elusive. LLMs can still hallucinate or miss answers, and no current solution guarantees 100% accuracy. It's important to set realistic expectations and understand that memory layers reduce, but do not eliminate, these issues. As research continues, we can expect improvements in scalability, evaluation, and security. For now, experimenting with different frameworks and architectures is the best way to find what works for your application.